Okay, first thing that we talked about so far is the idea of a sampling distribution. So sampling distribution as a whole, we said it shows all the possible values of a statistic and how often they occur. The big deal is that if it's a dot plot, let's say each dot represents a sample, not an individual. One of the big things we talked about that you saw in the warm-up is biased and unbiased estimators. So what we're going to do for the last kind of half of this unit is specifically we're going to look at proportion and mean. The reason we choose those is they are both unbiased. So sample proportion is an unbiased statistic that we calculate for a categorical variable, whereas sample mean is an unbiased statistic for a numeric variable. All of second semester, everything is going to be sample mean, sample proportion. And again, that's because these are both measures of center. They're unbiased, one for categorical data, one for numeric. So this is where I need you to be currently. We're going to take a look at the Candy Machine applet again, and so I'm going to pull up the applet. You all are also going to pull up the applet eventually. But what we're going to do is take a look at what is the applet. We're going to talk about the sample, the sampling distribution, and the individuals. Now that we reviewed the applet, let's talk about the population, the sample, the sampling distribution, and the individuals. Okay, so first of all, individuals. Of course, is the candy. Each individual piece of candy. The population is all the candies and their individual colors. Sample would be the candy colors for one sample of size n equals 25. And then the sampling distribution is every sample of size n equals 25. Specifically, it is the proportion of orange candies. For each sample. Okay, this individuals, that's not really what I meant. What I meant for us to do is to indicate what are the individuals in each distribution. So in the population, what are the individuals? In the sample, what are the individuals? In the sampling distribution, what are the individuals? In the population, the individuals are the individual candies. So every candy is an individual. In the sample, same thing. Every candy is an individual. In the sampling distribution, though, in our dot plot, every dot is a p hat. And p hat represents sample proportion. So here's what you are going to be doing. You and the person next to you are going to do all 6 of these graphs. So for each graph, it tells you what sample size and what proportion of orange candies there are. I want you to take a screenshot from the applet that also shows the center and spread. So you need to check the box that says show summary statistics and then put 6 graphs up here. And what I want you to tell me is what is happening. So across the top row, what is changing? Across the top row, which number is changing?
The proportion that's on orange.
Yeah, do you guys notice that the top row is all n equals 25 and it's p that's changing? So I want you to be thinking, as p is changing, what's happening? Does it change the center? Does it change the shape? Does it change the spread? Then we go to n equals 100. When we change sample sizes, what happened? Okay, so take, I don't know, let's say 8 minutes with the person next to you, get all 6 of these, and then what is happening in the center, shape, and spread as p changes and as n changes? What did you all see as top line as p was getting bigger? What happened to the center? It increased. Could we predict the center? What was the center of the first distribution around? 0.1. 0.1. What about this one? 0.9. This one? 0.9. Okay, so did we see that in all 6 distributions, the distribution is centered at the true value? Right, so that shouldn't have been a shock. That's because sample proportion is unbiased. What happened to the spread as p went from 0.1 to 0.5 to 0.9? Bigger, smaller, both?
Bigger.
So it got bigger from here to here,
Smaller.
and then it got smaller again, right? So spread got bigger, then got smaller. Okay, and then what happened to the shape? It was skewed here. What about when p is 0.5? More symmetric? Okay. When we went from n equals 25 to n equals 100, did that affect the center? Shouldn't have. Should have been around 0.1, around 0.1. Did it affect the spread? Guys, come on, give me something. When we went from the top row to the bottom row, did it affect the spread? Yes, how so? Smaller. What happened to the shape? Should have been skewed here, but then maybe more symmetric here. Okay, we're going to write all of that down and formalize what you all just discovered on the next page. Okay, so the first thing, when is it okay to say that the distribution of p hat is approximately normal? So the distribution of p hat, and remember p hat is sample proportion, is more normal or approaches normality when n is large and or p, which is population proportion, is close to 0.5. Now, of course, that is generic. We need a rule to go by. So our rule is NP has to be at least 10 and N1 minus P has to be at least 10. Both of those have to be true. As long as both of those are true, the distribution of P hat then is approximately normal. So then that's the shape part, talking about center and spread. The center of the sampling distribution. So this is the mean of the sampling distribution of p hat. That's what that symbol means. That is equal to the population proportion. And again, that is because p hat is unbiased. All we are saying is that if we took all the p hats of the same size, like all the samples of size 100, and calculated the sample proportion, some are going to be bigger than p, some are going to be smaller than p, but in the long run, we will be centered at the true value. And then the spread, so that is the standard deviation of the sampling distribution. That is the square root of p times 1 minus p over n. It is incredibly important that you know the difference between p and p hat. P is population proportion, p hat is sample proportion. For that second formula to work, this is only when sampling with replacement. Bless you. How often do we sample with replacement? Never, pretty much never. Do you guys remember the rule as to when sampling with and without replacement are pretty much the same? They're indistinguishable. When your sample size is less than 10% of the population size. Okay. We have one example to do, and then we are done with notes. We will take a break and then do some examples. Fair? Okay. The superintendent of a large school district wants to know what proportion of middle school students in her district are planning to attend a 4-year college or university. Suppose that 80% of all middle school students in her district are planning to attend a 4-year college or university, and the superintendent randomly selects 125 students. A, calculate the mean and standard deviation of the distribution of p hat, and then interpret standard deviation. Okay, first thing to notice is what these numbers are. 80% and 125. We need to label those numbers. That 80%, it says 80% of all middle school students. So that is a population parameter. That is P. That tells us that P is 0.8. And we are taking samples of size 125. So the mean then of P hat is just P, that's 0.8. The standard deviation of P hat, that is the square root of 0.8, 1 minus 0.8, divided by 125, which is about 0.036. And again, I need us to remember what we're thinking about is if we were to take samples of size 125 over and over and over again. And we were to put each one on a dot plot, that would be the center and spread of that distribution. Okay, if we interpret that, this is going to be, of course, in the long run, if we repeatedly sampled 125 middle school students in this district, and reported the sample proportion, planning to attend a 4-year college or university, the sample proportion would typically differ from the average or mean by 0.036. So if we were to take a whole bunch of samples of the same size over and over and over again and calculate a sample proportion, this is the typical difference between that and 0.8. One thing I forgot to mention. This calculation is only true if our sample size is less than 10% of the population. And we do need to check that. We don't have the population size though. We only have the sample size. So we know we're taking samples of size 125. So that has to be less than 10% of our population. So if we divide by 0.1, I get 1,250 has to be less than n. So this is saying our population has to be bigger than 1,250. We don't know that, but we do know that it is a large middle school district. So what we're just going to write then is this is a reasonable because it is a large middle school district. So anytime you use the standard deviation formula, you're going to have to do that.
Is that something we can do in a pad, or we need to write it down for credit?
Write it down. Question was, do you have to write it down? Yes. Okay, I need like 4 more minutes and then we're done with notes. B, what is the probability that a simple random sample of size 125 will give a sample proportion of at most 75%? Okay. In probability notation, we are looking for the probability of a sample proportion less than or equal to 0.75, not 75%. Sample proportion is always between 0 and 1. So what we know so far is we know the mean of the distribution and we know the standard deviation of the distribution. Those are not helpful unless we know the shape. So what we need to know is p hat normal? The way we do that is we look at n times p and n times 1 minus p. So this is going to be 125 times 0.8, which is 100. That's definitely greater than or equal to 10. Then we need 125 multiplied by 1 subtract 0.2, which is 25, which is definitely greater than or equal to 10. And so what we now know is that p hat has a normal distribution. We know the mean of p hat is 0.8 because we already calculated that. We know the standard deviation of p hat is about 0.036. So now it's just a plain normal CDF question. Anytime you use normal CDF or a normal distribution, what do you have to do? Like, what have I not done yet that I would want you all to do?
You either write out like the probability value or you draw a photo.
Okay. I would like a figure. Last thing I want you to do is pull out your calculator, please, and calculate that probability. This one. Probability that p hat is less than or equal to 0.75. So you're going to use normal CDF. Here's your mean. Here's your standard deviation. I got about 0.0824. You all agree? Okay. So, to get full credit, you need to show the calculation as to why p hat is normal. You need to write out the normal statement. And you need to show probability notation with a number and the direction you are shading. Now, like Rosie said, both of these can be communicated in a figure instead. So if you draw a well-labeled figure, it will communicate those two ideas. We have one last thing to write down, and then I promise we're actually done with notes. That go okay? Okay, last thing that I want you to write down. What do? If the normality check is not met. So if the normality check is not met, we cannot use normal CDF. We have two options. The first option is we would do a simulation instead. Now, we're not going to do a simulation and carry it out, but like that's what statisticians would do. Second option is we could use the binomial distribution. Assuming the assumptions for that are met. That's what I have for you. Questions for me?